This is a production of Cornell University.
Today I will talk about the application of the pre and post-harvest BGRs to manage the quality, maturity, and shelf life, longevity for the horticultural crops, fruit and vegetables. And just to start with a brief introduction about myself. I am Yosef Al Shoffe. I am Senior Research Associate. I have been here at Cornell in SIBS in the department since 2013. And originally, I am from Syria. And this here, Syria, if you are not familiar with the country, most of the land, 50% or over, desert. I am from southern part of Syria, named as Suwaida city, which is mountain. If you see the green on the top here of the area, it's around 80 miles southern part of Damascus, and we have because there is mountain, the elevation from 2,600 to 5,900 foot above sea level, which is has like very rich volcanic soils. We have 4 different seasons, very nice spring, and also we get some snow in the winter. For that, we have in the high elevation, we grow apples and a grape, table grape, and also wine grape in our area. Besides, in the low elevation, we have some olive trees. I got my bachelor degree in science in horticulture, agriculture in 1999 at Damascus University. And after that, I moved to Egypt to do my and did my master science in pomology, and I worked on table grape in the Egyptian desert here. The grape, which is like unique area to produce the table grape because it's produced too early, has very high price in the market worldwide. And I had the opportunity to visit the pyramids and Sphinx and all parts of Egypt for 3 years there, which is really fun. And I got my PhD at Damascus University. In horticulture, the same. I worked on table grape again, but during my study, I had the opportunity to visit Hohenheim University. I was working with Professor Jans Wonschi. Sadly, he passed away. He worked in crop science, crop physiology, and at that time, I worked on high density orchard, the first time in my life, and it was on organic, Kanzi, and tubers. And I involved in different lectures and field trips with Wonschi's team. And also the opportunity was great to visit the Mercedes Museum there, which was really nice and fun beside different parts of Germany. Then in 2013, as I mentioned, I came with Chris Watkins. I worked as a postdoc for a few years. Then I, with support of Chris, I promoted to senior to research associate in 2016, working in post-harvest. Then in 2022, I have been promoted to senior research associate. Now my position is 80% research and 20% extension. And just here, part of my our socialization with during the ASHS conference, our great people in the horticulture department, which always I am proud to be a part of this great people and great section. The same, our team in the lab. And also I had the opportunity to teach botany class in TC3. At that time also, it was very nice to expose the students in TC3 to what we do at Cornell. They had the opportunity to visit the Cornell orchards, and Jay, he did a great job to just also explaining to them about what we are doing. Also, they visited our lab and medicine lab. Then starting with the topic, as I mentioned, I will explain about or speak about the plant growth regulators in relation to the pre and post-harvest management of fruit and vegetables in perspective of the post-harvest science, which I have now working on this field. And Now I am in horticulture department, which is most of you, they work already on many of these hormones, and they know better than me about these natural phytohormones and their impacts and interest in the plant, which is they classified to different classes. They react in small concentration for the growing and development of the plant, starting from the seeds to the flowering and the fruit, which is really essential and important as igniters or inhibitors to many pathways. And today, as I mentioned, I will focus on ethylene management, about the pre and post-harvest plant growth regulators in managing ethylene production in fruit and vegetables. And as you know, like ethylene can interact with antagonistic or synergistic effect with different hormones, such as abscisic acid or gibberellin, whereas with cytokinin and auxin, the reaction can be sometimes fluctuated based on the time of the physiological stage and based on the plant organ. And based on the management of the ethylene and fruit physiology, we start with fruit maturity at harvest, which is usually we pick the fruit and vegetable, as most of you know, based on certain parameters, use the primary and secondary metabolites, which we name it as maturity indices. And those, the maturity indexes here, indices, we rely on respiration, ethylene production, the flavor, texture, color, pigments, volatile, aroma, flavor, and acids. And like in combination, all these compounds, they contribute in having the consumer preference and consumer acceptability, which is the main goal of handling of these crops in general. And based on ethylene production and the pattern of the respiration in the plants, we can classify the crops into two groups, as a climacteric and non-climacteric fruit. And this is, I think, very like known for most of you. The climacteric fruit, which means that we can pick the fruit in a specific maturity stage based on the goal of marketing and storage. But the fruit or vegetable, they can continue ripening during the storage. However, non-climacteric fruit, we have to pick it in a specific ripening stage. And this curve, it's like taken from the Valent 2019. If you see in the x-axis, the cell development from the cell division to the senescent breakdown, we have a climacteric in solid line, non-climacteric in dotted line. We have the respiration in red and ethylene in blue. And if you see from the maturity to ripening, the red, the respiration, and the ethylene can rise up, which means the fruit continue ripening. But in non-climacteric fruit, they stay very low concentration, even stable sometimes, based on the cultivar and the species. And if we will handle these fruit perfectly, or the vegetable, this gap actually is the best time to keep the fruit quality, to apply any post-harvest management, which we can manage the quality of the fruit or maintain this quality to have good shelf life. After that, the fruit, as you said, like they go to senescent breakdown. We have to market the fruit here, and based on the peak of the higher respiration and higher ethylene production, we can have this as the buoyant, which converted from the maintaining ripening toward senescent and aging of the fruit. And there is like, those can be measured, as you know, from gas chromatography. And recently I contributed in book chapter about ethylene sensing and signaling. You can find the data or the method about how to measure internal and external ethylene concentration. And fortunately, this is open access from Cornell. You can have it as well if you are interested. Always the reality is not like, you know, the facts in the real time, right? You know, it's some fruit, they can behave as climacteric and non-climacteric, such as the grape. In the grape, the clusters themselves, they can be, the clusters, they classified as climacteric. They have ethylene production and they have respiration. However, the berries, they classified as non-climacteric. And in this paper, the superior seedless in the top and red globe, when they put it in the air for 28 days, the clusters, it's like brown now. But when they applied 3 days of 20% of carbon dioxide and they stored it in air storage for 25 days, the cluster still fresh and green. And this is one of the important factors of the quality to sell the fruit. And the same experiment here in response to 1-MCP as a post-harvest 1-methyl cyclopropene, which is ethylene inhibitor, plus and minus here, two treatments. This is the H2O2, which gives the oxygen, 80% oxygen, 20% carbon dioxide. In the end of the storage for 32 days, is very clear impact on the MCP with different treatments compared to control to maintain the quality of and the freshness of the clusters. And more complicated as well, if we will go to the genotype. In different genotypes, even in the same species, there is varied in the response or pattern for the climacteric and non-climacteric fruit. In the left here, we have 4 genotypes. If you see the square here, SC35, behave as climacteric, having ethylene and respiration production. However, the 3 non-climacteric. The same other 4 genotypes here, one of them, the M5, M7, non-climacteric, very low ethylene concentration and respiration production. In the Japanese plum, also different cultivars in the same species here, they have different pattern. In Santa Rosa, it responds to ethylene inhibitor, MCP, 1-MCP, or promoter, the propylene, which cause the ethylene production. And very clear, the response of increasing or decreasing the respiration and ethylene. However, in the sweet Miriam here, no response for ethylene production from inhibitor or promoter. And recently, we are working on papa fruit. This is indigenous fruit, and I think Griffin just arrived now. And this is Griffin worked on this project, and this is funded by TSF towards sustainability fund from the department. And the papa fruit classified as climacteric. And when we applied the 1-MCP on papa, and we stored the fruit for, I believe here, for 35 days, if you see the ethylene production is still low. And sometimes here in MCP, the response was opposite to what we expect. In respiration, the same. It was stable during the storage, and it behaves now like as our finding as non-climacteric fruit, which like can share the story about handling and packaging of the fruit, even the storage for the fruit. Like in my opinion here, this should be stored on high carbon dioxide, low oxygen level in modified atmosphere packaging to stay more or longer. Then back to ethylene as a natural hormone. Just a quick background about ethylene. Ethylene is a gaseous hormone. It's olefin gas, C2H4, and it's the first hormone which like discovered. It's used by Chinese in 2000 year before century, which always you have a lot of progress in many things. And the first study about ethylene in 1896 by Dimitri Nilijobu about the triple response. And I'm sure you are familiar with this one. But back to managing ethylene, always when we need to manage anything, we have to know the best way. And by Yang cycle, the ethylene production starts from the L-methionine amino acid through SAMs, AC synthase, to give in the end the ethylene production. And tomato used always parallel with Arabidopsis as a model for studying the ripening in the fruit and vegetables. And if you see here, the ethylene can be classified into 2 systems, system 1 and system 2 briefly. System 1 is auto-inhibition of ethylene. There is some enzymes, ACS1A6 and ACO134. They inhibit the ethylene. And in the breaker stage in tomato, based on the color, the ACS24 can activate it and just move to auto-induction of ethylene until the same peak which we mentioned before, it goes toward senescent and reducing the ethylene production. And there is like a lot of methods that can be applied to manage ethylene, starting from the effect on the plant growth itself by applying chemicals and plant growth regulators. Some they are natural or synthetic hormones or different chemicals, and also genetic modifications, or by controlling the environment. We use now controlled atmospheric storage by lowering the oxygen level and increasing the carbon dioxide in the system, or modified atmospheric storage by packaging. We can also absorb the ethylene with different chemicals here. But today, we will focus a little bit about some examples of the plant growth regulators. And as we mentioned, there is like a lot of work has been done on managing ethylene. And what I will explain today, or have some work has been done at our lab about 1-methyl cyclopropene, aminoethoxyvinyl glycine AVG, 1-aminocyclopropene, 1-carboxylic acid ACC, ethylene promoter, and or precursor, and abscisic acid. And starting with 1-MCP, 1-methyl cyclopropene, it's really revolution in the ripening, control, and handling of the fruit and vegetables, especially for the climacteric fruit. And it's patented in 1996 by Sisler and Blankenship. And the mechanism of the effect of 1-MCP, it blocks the ethylene receptors here in the cell, in the cytoplasm, in the endoplasmic reticulum, which is this block actually irreversible. That means to continue the fruit ripening or the vegetable, they have to regenerate new receptors. And apple was the first crop which is registered to for the application of 1-MCP in 2001. And there is a lot of literature about that. And one of the interesting review article for Chris in 2007 about using of MCP, still very important in the literature. And in this busy table, just to show you in the climacteric fruit, in apple, pear, peach, banana, kiwi fruit, the pre and post harvest application of 1-MCP, which is there is one compound can be sprayed as sprayable compound before harvest, used to manage usually the harvest window, and another compound, 1-MCP as a gas, can be used in the post harvest, also the same reason to delay the ripening. It's with interaction with different storage systems with main different goals. I will not dig deep here, but just to show there is a lot of literature about using MCP in pre and post harvest. But also MCP, as we mentioned, as ethylene inhibitor, can be used in non-climacteric fruit. And one of the impact here, as we mentioned, maintaining freshness and the cluster green in grapes. When this study applied ethylene as a promoter compared to control and MCP gives more green and freshness to the clusters. In pomegranate as well as non-climacteric, also MCP reduced the chilling injury, the superficial scald on the skin of the fruit. And in the pitaya fruit here, the MCP prevented the oxidation and more freshness and shelf life. In the citrus fruit, this is the greening and degreening. When we have, or they have the MCP, it's improve or delay, sorry, the greening, converting to different, the chlorophyll to different pigments, which is increase the shelf life as well. In cactus fruit, effect on the shelf life of the fruit and improve the color, or also prevent the color degradation. In strawberry, the impact of the 1-MCB was not a lot in relating to the fruit quality, but it inhibited the botrytis cinerea, or gray mold. And Connor, in his publication recently about using retain different plant growth regulators which inhibit ethylene, also found that on Snapdragon apple, the application of retain or AVG, it's shifted, delayed the microbiome, the bacteria and fungi, in relation to the fruit maturity. I believe similar pattern here occurred. In low-cut fruit, the MCB compared to ethylene and control, when they put the fruit in the shelf life, the effect on reducing the shelling injury. In cherry, similar to what they found in strawberry, effect on the gray mold, effect on the stem pedicels here, more green, and also reduce the pitting, which is shelling injury in cherry fruit. Then we applied 1-MCB in pre and post harvest extensively in our lab, and Chris has great experience with MCB, as we said, like since 2001, since it's registered. And one important application I will present just a few from our lab, our work on Honeycrisp apple. As mentioned, Bill, in the beginning, Honeycrisp is very profitable cultivar, very important for the industry, and still #1 in the price in the market. And the problem with Honeycrisp, it suffers from the calcium deficiency, which cause bitter bit incidence. And also in the storage, if you put the cultivar in low storage temperature, it causes chilling injury as soft scald burn on the skin from the low storage temperature. We applied the pre-harvest as a Harvesta TM from AgroFresh and post-harvest Smart Fresh. And based on these details, but we put the fruit here in 33, 0.5 Celsius, conditioning plus 38 means 50 Fahrenheit for 1 week, 10 Celsius, then move to 3 Celsius or 38 Fahrenheit for 5 months plus 4 days and room temperature. What we found, this is from black susceptible to bitter bit. When we applied Harvesta increased the bitter bit incidence. That means the calcium deficiency. Moreover, here, the interaction with MCB as a pre and post harvest exacerbate what we name it as leather blotch. And this is very also brown, dark spots here will be in the skin as a burn, effect also on the marketability on the fruit. But surprisingly, we found that Harvesta reduced the shelling injury significantly with control and treated fruit in 0.5 Celsius or 33 Fahrenheit, which is really important to know the great impact. No impact of 1-MCB, only the pre-harvest MCB. The same compound, the time of the application is different and gives like different impact on the fruit physiology during the storage. But the MCB always not like magic bullet, we have to use it in every time. And nowadays, the growers and the warehouses, the storage operators, they use MCB as recipe, just they have to MCB everything. The reality is different. In our crisp apple, this is high-value cultivar, new breed from the Midwest Apple Association program. It's a breed from Honeycrisp and Fuji, and susceptible to different disorders because it's inherited from Honeycrisp a lot of bad and good things. But we found that the core browning, as in this photo, is induced or improved by MCB application. And first, this call came from Hess brother, Ryan Hess, from Pennsylvania. They had a problem in the browning during the storage on this cultivar. And when we stored 8 different blocks here in 2 different temperatures with and without MCB, no MCB is a blue. And we found in 4 months of storage, the browning started to show in the MCB treatments. And when we delayed the fruit for 7 months of the storage, the increase of the browning was 100% in some blocks and started to show in 33. That means now we know that MCB, our recommendation, doesn't work on this cultivar. We don't recommend MCB to be applied on our crisp apple. And also the storage temperature in interaction with MCP and no MCP is now 38 as recommendation so far. Then shifting gear to other compound, the 1-amino-ethoxyvinyl glycine or AVG, commercialized as Retain. This is from Valent Bioscience. And the mechanism of working here is different. It blocks the ACC synthase in the ethylene production, which impact mainly used for the delaying the harvest window, expanding harvest window, having the time for the facing the shortage in the labor, very important now in for the growers. What it does, like this abscission zone can be delayed and can be sometimes delayed for 2 weeks. And in this time as well, the fruit can continue growing. And this patent actually in 1973 and registered also in different countries except Europe, which is also the regulation in Europe, as like in previous presentation I heard, it's always complicated. Then the same, there is tons of publications about the pre-harvest application of Retain, and most of these to manage the harvest time in relation to the post-harvest management. But our also work on Retain is really huge and big. And I will just have a little bit of information about the Retain in managing stem end flesh browning in Gala apple. And Gala is breed from New Zealand, I believe in 1930 start, and entered to US in 1960 to 70, and become now the most popular apple cultivar. More than 45 million bushels produced in US, 18% of total production. And our team, Liliang, Terence, and others from the pre-harvest and Greg, did a great job in managing the fruit crop load and the fruit quality in the pre-harvest. But the problem is still in the post-harvest about the stem end flesh browning. This starts in the stem end area, expand during the storage to the shoulders, the flesh, the core, and into the calyx end, which cause a lot of damage. Sometimes more than 70% of the fruit can be damaged in this disorder. Then, as we said, like many trials and work has been done before we applied Retain to just understand the mechanism of this disorder, and we found mainly the fruit maturity is the main cause or inhibitor for this disorder. Then, as we said, like AVG or Retain delay the maturity. We applied Retain in different concentration and different time, starting from 1 month before harvest. Plus, here also we compared with pre-harvest 1 MCP. We picked the fruit in 3 harvest time, early, commercial, and late, and we stored it in controlled atmospheric storage, 2% oxygen, 1% carbon dioxide for 8 months plus shelf life. And I will not dig deep to what we found, a lot of data, but the most important thing, the fruit quality. Fruit quality from this BCA plot, harvest 1, 2, and 3 in different colors, is very clear that firmness and IED value, which reflect the chlorophyll content as non-destructively, it's maintained based on the harvest in combination with all pre-harvest PGRs. But if you have these open circles, they are control. Control increase the internal ethylene concentration plus the flesh browning. And to zoom on here, very clear, the blue is control, increased by the harvest time. All the PGRs in different concentration and timing reduced or delayed the browning in Gala apple, which is a very now strong recommendation for the growers to use pre-harvest ethylene inhibitor, Retain or harvester. But also the same, like we found that MCP sometimes has negative impact based on the cultivar and genotype. Similar here, the application of Retain or harvester can cause issues in some cultivars. In Ruby Frost, New York 2, it's from Susan Brown breed. It's very attractive color, very white flesh. It's used for a fresh market and fresh cut. But this cultivar is susceptible to superficial scald. And this is oxidation on the skin of the fruit in the unblushed side of the green side, which can be managed usually by applying post-harvest MCB, DCA lowering the oxygen. Any treatment can inhibit the ethylene, can reduce or prevent the superficial scald. And this is like we built our hypothesis based on that. We said like AVG or Harvesta, MCB as a pre-harvest might be working to reduce the superficial scald since they reduce the ethylene production. But and we applied 2 weeks retain, 1 week Harvesta, we picked in 3 harvest time, and the storage was only air storage in 0.5 Celsius for 20 weeks. The alpha-farnesene, this is the compound, it's actually the secondary metabolized, the volatile, increased, it's responsible for the browning or superficial scald, increased during the storage and peaked in 6 weeks here in all treatments. But the oxidation of this product, cetols, or this is the main cause of the browning. We found its peaked, or the highest was in 10 weeks and was in AVG treatment compared to the other treatments. But when we have the scale of the superficial scald from 0 to 3, it's very clear that the incidence and severity always high in retain treated fruit compared to control and harvester. And you can find more work or more information in Science and Horticulture if you are interested. Just now, to also change the crop itself, we recently working on the ethylene inhibitors, ethylene promoters. And the main goal from this work on blueberry is to improve the color. And this is with Marvin and supported by Valent Bioscience. And we selected Duke here from Cornell Orchards. And our goal and hypothesis is that if we promote the color in the clusters, it can be easier for mechanical harvest first, also to reduce the number of the harvest picking of harvest time. Instead of harvest 3 times, we can harvest 2 times. Then we applied ACC here as ethylene precursor, abscisic acid as a proton here, and exceed commercialized. This is 1 week, 2 weeks, and 2 weeks before harvest. And at harvest, we found that the number of the colored fruit in the cluster was improved by ACC mainly. In the ABA, a little bit improved, but there is no significant difference between the control. And thank you, Marvin, for the support as well. The fruit shriveling also was affected during the storage time. We stored the fruit here at 33 Fahrenheit for 38 days, and we did different times for shriveling. After 2 weeks of the storage, the shriveling started, but if you see no decay at all was found even after 38 days of storage. The shriveling was reduced by ABA, around 19%. The other work which we are doing now on sprouting on onion. And you know, always the sprouting is big issue for marketing of onion, also for the quality of the bulbs, because it causes, as in this photo, a lot of weight loss, and the fruit or the bulb will lose a lot of energy and compounds from it. Then we measure the sprouting here by measuring the stem here, the green one, compared to the length of the bulb. And this work, in collaboration with Christy Hopting from CCE and supported by Restrain. This is a company located or originated in Netherlands. And they have this technology by converting ethanol to ethylene, as exactly happened when we ripe the banana fruit. They catalyze ethanol to ethylene, and there is a sensor, very nano sensor, which can also measure the ethylene production rate and respiration as well. And we compared this work as continuous ethylene production during the storage with pre-harvest malic hydrazide as a common use BGRs on reducing the sprouting in the onion. We selected 2 cultivars based on Christie recommendation, Hamilton and Red Wing. It's clear here from during the storage, the sprout increased by the time. It was from the beginning higher in Red Wing compared to the white, or the Hamilton, or the yellow. But in general, no significant impact on any of these BGRs, Merikidrazide, compared to any of them compared to control for 7 months. But when we put the fruit, actually for shelf life, we put it for 2 months, and we did just different times. It's not exactly weekly. A few times we have the times, but actually what we found in conclusion here, that the ethylene with Merikidrazide have significant effect, synergistic effect together in reducing the sprout percentage, even in the red cultivar to 0% here. But if you see the Merikidrazide and ethylene were fluctuated in their response on the sprout. And just to conclude my talk today, the BGRs as a blend growth regulators, they are very essential now in managing the harvest time and post-harvest as well. But the time and concentration is essential to know exactly when we have to apply it and why we will apply it based on the management plan of the harvest and post-harvest. Also, we have to know that the cultivars and even genotypes can greatly differ in their response to the blend growth regulators. And this is not only on ethylene, on all primary and secondary metabolites. We have tons of data, but only we presented what we have about ethylene today. In the end, I would like to thank Chris Watkins for having me in the lab for now over 12 years, for his support, and also our great team. Before Jackie Neck was the technician in our lab, the postdoc, the visiting scholar. We have, more than 50 people during this 12 years. They have, like now with us, not only colleagues, we have friendship with them. Also, Caspar, Griffin, Brian, the great people in the orchard, very helpful, Jay, Eric, and Mike, our collaborators from the industry and Cornell Cooperative Extension, our faculty here, great people, the private, state, and the federal fund for the support of the work. And thank you for your attention, and open for any question. Any question?
Yosef,
yes.
Can you talk about regulation of post-harvest use? What bodies regulate that, and maybe what cost inhibit for certain crops?
Yeah, that's a very good question. Always the ABA and FDA contribute to regulate the applications of the blend growth regulators, and they classify it sometimes when we report as pesticide. That means they are not pesticide, but we report them when we work in the pesticide report. And those classified actually as pesticide report. For one MCP, as example, there is 1 ppm limit in post-harvest. That means we have not to exceed 1 ppm in the storage area. For the AVG or retain, also there is specific concentration based on the acre. That means the 1 pouch per acre or half pouch per acre. This can be applied based on the time, 28 days or 15 days before harvest. Based on the time of the application, also the residuous effect is calculated there and regulated by the company and through the company and by FDA and EPA. The same for the other compounds. The ACC, since it's a precursor naturally occurred in MCP and EPA also naturally, there is no certain concentration, but they are very expensive. That means the application is limited for 100 to 100 ppm based on what we will use.
If I understood you correctly, you have seen genotypic differences in the response to MCP.
Correct.
In some instances, MCP is not effective. And do you think that's because the receptor structure differs and therefore the MCP isn't binding to the receptor?
That's, yeah, very good question. Yeah, sometimes the ripening stage, as you said, is very critical time to judge this point, right? That means if the receptor is already blocked with ethylene, right? That means MCP will not work. And this might happen in the papa fruit, right? But we are working on this as well. Like I did apply ethylene as inhibitor and MCP after that, but still the same response. We did collect the fruit in different harvest time, still the same response, like very low. But again, for the apple as example, this is very true. The harvest time, when you harvest too late, then the response of one MCP will be different compared to when you harvest on exact timing. For that, measuring ethylene for some climacteric fruits such as apple is very important indicator to know exactly the onset of the apple. Based on that, we can have it and apply the correct amount of MCP. But sometimes the color is major driver for the quality. For that, the people, they will not pick the fruit early without development, very red color, and based on the market demand and also what the market need. For that, maybe the maturity will be changed and the ethylene will be increased. Then the response of the post-harvest MCP will be decreased. Yeah, thank you so much. Any question? Yeah.
You mentioned nanosensors for ethylene in your onion work.
Yes.
Could you describe a little more? Like, can you embed the sensor into the onion?
Oh, no. Just like, the material itself, which used as a sensor inside the sensor, they are nanoparticles. Yeah, not inside the onion itself.
Oh.
Yeah, sorry for the confusion. But also it has another sensor for carbon dioxide. Any other question? I have a question maybe for Marvin about the blueberry, our work on blueberry here, right? We found the application of ACC as ethylene precursor improve the color in Duke blueberry, beside the ABA as well. Do you think this is commercially has like good impact on, as we explained, and our hypothesis rely on this?
Yeah, I don't know. I think that a lot of people feel like it's the wax on the fruit that gives it the desirable appearance, not so much the base color.
Okay.
It's how much wax is on there. So I don't know if you separated out the pigment from the wax, but that might give you a clue as to what's going on there in terms of color.
I see.
Because normally a blueberry is almost black, and that wax makes it look blue. And for consumers, the bluer, the more desirable. But it's because of the wax.
I see. Yeah, we classified it based on the percentage of the color compared to green and blue or black. Yeah, any question? Thank you, Marvin. Yeah, thank you so much. Yeah, thank you.
This has been a production of Cornell University, on the web at cornell.edu.